We're going to be talking about software supply chain security, a sandwich that goes well with GUAC. Before getting into it, a few things about myself. I'm the co-founder and CTO of Kusari, a software supply chain security company. But before that, I worked at a lot of end user companies in the fintech and banking space. So nowadays, I'm doing a lot of building security tools, and in a previous life, I was doing a lot of work in consuming security tools. I'm also the co-author of Securing the Software Supply Chain, a book being published by Manning a little later this year. I'm also heavily involved in open source, being an OpenSSF governing board member, as well as technical advisory council member. I'm also involved in the CNCF, being a tag security lead. So that's tag security is the technical advisory group for security underneath the CNCF. And for folks who are not super familiar with OpenSSF and CNCF, they're both foundations that fall underneath the Linux Foundation umbrella. And OpenSSF stands for the Open Source Security Foundation, very much focused on securing open source approaches to securing software. And the CNCF is focused on all things cloud native, so think Kubernetes, containers, that kind of thing. I'm also a maintainer of various open source projects, including GUAC and Salsa. Those two projects both fall under the OpenSSF. And the QR code here at the bottom is a link to 3 chapters from that book, the Securing the Software Supply Chain, that should be coming out later this year. Let me start by saying it often seems like no matter how much progress we make in securing the systems and services we build, everything can often feel like it's always on fire, right? There is some new major attack or major vulnerability being discovered seemingly at least once a month. There was the XZ attack back in March, where a malicious actor, most likely a state-sponsored one, added a backdoor to XZ, which XZ is a compression library that is used by lots of other tools, including OpenSSH. And this backdoor would compromise OpenSSH in certain contexts because OpenSSH used XZ as a dependency as part of its build. Since then, there's also been a lot of other major vulnerabilities. Most recently, the one that comes to mind for me, at least, is just a few weeks ago, there was the JavaScript polyfill library, right? Their maintainer, unclear exactly who that is in reality, introduced malware to the polyfill library, compromising potentially hundreds of thousands of websites. So, how do you make sense of this, right? So this over here, right, this is just a list of some of the most recent vulnerabilities as listed through the GitHub API. You might look at these vulnerabilities and think you might not be exposed, but how do you really know, right? You might be tracking these dependencies. You might be, looking through your requirements.txt or your packages.json, and you might say, hey, none of the stuff that's in this list is something that I use, right? But how do you know that the software you use doesn't somehow use that somewhere down the line, right? It can be very, very difficult to figure this out. And there seems to be a new list of vulnerabilities that are coming up almost every day, right? So let's take a step back, right? What is sort of supply chain security really, right? We'll see in a moment, right, that supply chain security is really just about securing all the things around producing code, right? And if you're on the other side and you're not a software producer, it's about essentially securely consuming other folks' software, right? Right. Now, let's go back to basics. Right, here is a threat diagram coming from the Salsa framework that I really like, right? For those who aren't familiar with Salsa too much, it's a framework of practices focused on ensuring the provenance of software is safe and secure. By that, I mean it's not intended to prove that, the software being written or built is itself intrinsically safe and secure, just that you have a level of trust that the metadata about the origin of the software is accurate, right? So if you ever need to go back and investigate the software, you have that information, right? So it's not about saying, hey, there's no there's no SQL injection attacks or anything like that inside the software itself. Just that, hey, if there is a SQL injection attack inside of a potential SQL injection vulnerability, I should say, inside the software, that you could go back and know exactly what commit that was introduced in, that sort of thing, right? And I believe like this threat diagram does a really good job at explaining the majority of supply chain security related threats. Pretty much anything that starts with a developer writing code and through to a consumer ingesting that software in some way, whether it's a library to the software you're developing, or if you're consuming a standalone tool, it's all within the realm of software supply chain security. And so if we go back again, right, like there's all sorts of vulnerabilities, A through I here. So let's actually now go in and take a closer look at what at those potential threats, right? And there'll also be some examples. So if we go and look at the producer, right, the producer of the software, can be malicious. They could put something, they could just be not well trained and introduce stuff like SQL injection vulnerabilities. But let's look at the case of XZ, right? You had a malicious actor going by most likely the pseudonym Jia Tan. This was a malicious actor, or most likely a team of malicious actors posing as a good Samaritan trying to help a project out, right? They then injected malicious behavior into test code that embedded itself into the downstream build process, right? And only really affected stuff like OpenSSH. Next up, we have issues that come up during things like the review process. We just saw this also recently with the OpenSSH regression bug that reintroduced a previously fixed vulnerability due to a change that wasn't caught in code review, right? So there was a vulnerability that was introduced years and years and years ago. They had fixed it. A new change in sort of refactoring some of the code had reintroduced that vulnerability, and it was not caught in the review process. The source code management systems, right, that we use, think GitHub, right, can be compromised in various ways. So malicious code might be introduced, right? For example, if folks are familiar with CodeCov, right, or if you're not, the CodeCov situation was where GitHub credentials were compromised and malicious code was added to the repo, poisoning everything downstream, right? So again, if we kind of go back to that producer, the producer themselves can be malicious, or their credentials can be stolen, or some other, or their repo can be hijacked in some way, and they can get, and malicious or vulnerable code can make its way in that way as well. As code moves from source code repo to the build, various things can go wrong here as well, right? The parameters or flags sent to CI tools you use can lead to the introduction of vulnerabilities. For example, a QA flag ending up being built into the production artifact. We've seen that sort of thing happen all the time. Or a dev flag being built into the production artifact. A real world example of this is the Debian OpenSSH crypto bug from something like over 15 years ago, right? A change a Debian maintainer had made to the code specifically just for the Debian OpenSSH package introduced crypto vulnerabilities. This was, a couple of details there. Just, hey, the amount of they were not, they were not using enough entropy for for generating the keys. The build process itself is probably the most sensitive to attacks in all of these threats. This is where most of the code gets transformed into a package or compiled artifact, right? This transformation can be very difficult to reason about. Whereas previous steps, you can usually look at the source code and introspect on what's going on. Once you've built that artifact, that has often been obfuscated. That the build itself will often obfuscate the code or transform it into a binary where it's opaque. Like you don't actually, you can't. It's very hard to relate that compiled artifact back to the software, right? I should say the code that makes up the software. And often you have to trust that the build process is in fact taking that source code and doing the right things and turning it into a package or artifact, right? Everything to the right of the build process, you can also at least check that the provenance of that artifact did come from the build process by verifying things like the hashes. A real-world attack example is the famous SolarWinds Sunburst attack, right? This is where an attacker compromised the build process itself, injecting a DLL into the build process. And since it was difficult to detect, everything around that build process, like the software signing systems, viewed everything as being on the up and up, right? Now, once software has been built, it usually gets published into some sort of artifact storage, right? Think, Sonatype Nexus, Artifactory, GitHub release, that kind of thing. A piece of software that didn't go through that build process we just talked about, right, could end up being published. For example, a developer might inadvertently push a dev artifact that they have locally into a production repo, right? Or we could see something a bit more malicious, right? We saw something like that happen in the past where someone had compromised the credentials for the event stream npm package, and they published a malicious artifact, right? Now, the package or artifact host itself, right, could be compromised in some way. A while back, Ruby gems got compromised through a vulnerability in the software they use to host gems, right? This led attackers to being able to publish malicious software without there really being any record that anything else had been compromised. They didn't need the credentials to anybody's repo. They just had direct access through Ruby gems itself. Finally, right, the user who is intending to download a specific package can be misled into downloading something else. This happens usually with an attack called typo squatting, right, where someone takes the name of a common package like Python's requests and changes a letter or two, and hoping someone will mistake it, right? Mistakes this sort of compromised package or this malicious package for the real one. This can have a compounding effect, since a consumer could still be affected by this, even if they don't type in, the wrong package name. If it turns out they use a package that package inadvertently used the typo squatted package, right? Now, all of these threats are things producers of software want to, prevent and make it easier to detect. And consumers want to also do that same thing, right? They want to better prevent and detect compromises when they ingest that and use this software that they're pulling from, whether it's open source or a vendor. Really, everything on the left-hand side of that previous diagram, if we just go back a second, has the ability to poison everything on the right-hand side. Okay, so as we looked in the previous section, anything that happens in a producer's SDLC, software delivery lifecycle, can impact a downstream's consumer's software delivery cycle, and this sort of problem continues on recursively. So it's turtles all the way down, as they say. I need to not just make sure that my immediate dependencies are safe, but those dependencies are safe, and those dependencies, and so on, right? If I'm writing a Java application, it's not just about the jar files I depend on, but it's also the JVM, right? It's also the libraries the JVM itself uses. I need to make sure that the operating system I built on is running and is secure, right? Am I on a vulnerable version of the Linux kernel? Am I using vulnerable system packages? That kind of thing. If I'm using a VM to run this server, right, I need to make sure the hypervisor is secure. And if I'm using a container, right, I need to make sure the container runtime is secure. I need to make sure that the hardware is secure. Another big challenge here is a lot of what I described is not something you can fix on your own, right? You don't, if a piece of software you use is using a vulnerable dependency, it's often not a whole lot you yourself can do, right? If you rely on a dependency and it's vulnerable, great. You need to make the decision. If there's no fix for that vulnerability, what do I do about it? How do I mitigate it, right? And if that piece of software itself has a vulnerability, what do you do about that, right? And we can take a look at that in a second here, right? So this is a highly simplified view of a dependency tree. The vulnerability or compromise can be in any of these dependencies. In reality, this dependency chain is more, significantly deeper, probably dozens of layers deep. But let's look at a simplified view of it, right? So as I mentioned sort of the previous slide, you need to look at not just the dependencies you rely on, right? So here we have vulnerable dependency 2, and vulnerable dependency 2 might be something that, like it could be a Python library or a Java library that you rely on directly. But you might also rely on dependency 1, and dependency 1 itself doesn't have a vulnerability, but it relies on another vulnerable dependency, right? And that's really where the challenge is. If the challenge was just at the shallow level, it'd be really easy just to say, okay, great, I'm just going to scan everything at in my packages .json, in my my request in my requirements.txt, in my Maven POM file, and whatever. But the issue is the way that our software is interlinked is quite complicated, right? And not just the software that we're using with stuff like Python or Java, but you also need to look at the dependencies outside your ecosystem, right? As I mentioned before in the previous slide, if you rely on containers, then the container runtime becomes part of your supply chain. Your OS and hardware are part of your supply chain. And the same thing actually goes for the upstream SDLC of your supply chain, right? What happens if the software was built in an environment with a compromised version of Linux, right? Going back to the SolarWinds thing, like if you rely on SolarWinds, well, SolarWinds was built on a compromised SDLC, and so that had knock-on effects and impacts. Don't worry, it's not all doom and gloom. There's been a lot of work in bringing order to the chaos. In the open source community, there's been a whole bunch of white papers. There's books being written about this on how to start dealing with supply chain security. And there's also a ton of tools being developed in the space that will explore those in the bit. In addition, we're seeing work happening in the community, industry, and in the government space as well. Now, we could sit here for days talking about all the approaches and potential solutions to all the supply chain security problems we have. We don't have days, so let's just look at some of the common things, shall we? All right. So it's really just like regular security. So approach supply chain security like regular security. So if I'm building my personal project, if I'm building a personal project like my blog, I'll have a very different approach to software supply chain security than if I'm building out an online banking application. If it's my personal blog, I'll take reasonable efforts, right, to make sure I'm not doing anything dangerous or pulling in obvious malware. I'll make sure my OS is up to date and I'm building using something like GitHub Actions instead of building on my local laptop. I'll make sure I'm running some tooling to see if I'm using up-to-date packages, right, that are not vulnerable. If it's an online banking application, on the other hand, I'll be spending a lot more time, resources, and effort to secure the software supply chain. I probably also have access to significantly more resources as well, right? Most likely, the bank will have multiple sort of systems running internally to help with vulnerability management, dependency management, firewalls, all sorts of stuff. Each dependency that gets pulled in will probably go through a lot more rigorous checks like SAST and DAST scans. Each version of a dependency will usually go through some sort of certification process. There will be defense in depth with various network security controls like a firewall to ensure that even if there is something vulnerable or compromised and is trying to exfiltrate data, right, it would get blocked. And that malicious behavior would be detected and be forwarded onto a security operations team, right? Now, this high-level approach, right, will stay even if the details change depending on the use case, right? So as I mentioned before, you want to start approaching this like you want to threat model your SDLC, right? If I'm running my personal blog, I'm threat modeling my SDLC. If I'm, building an online banking application, I'm probably doing it a lot more rigorously with a lot more resources, but it's still the same general approach there, where I'm trying to figure out what the threats are, what are the things I want to protect, how do I design sort of mitigations against those risks, and how do I implement those, mitigations or controls. Okay, so you probably have some questions running through your head based on the previous slides. You're probably wondering what you can do to get started on today that helps with the sort of average use case. So, you might say, great, I'm, just running a normal application. We've done a basic threat model. It seems like everybody else, right? So, you care about security, but you're not, looking to prevent progress. You're not looking to hold up feature work, that kind of stuff either, unless you have to, right? There is a major issue that was detected, right? So you want to be safe, but you don't have the resources, for example, to build the Linux kernel from scratch. Most importantly, though, you're probably wondering how if any of these security measures are actually working. Okay, so it's really about knowledge. A core bit of all cybersecurity is about tracking what's happening in your systems. You want to track network traffic to determine anomalies and stuff like that. The same is true for software supply chain security. However, it's much less mature right now, at least compared to network security. We want to track software as it makes its way from developer through to consumption and all the layers throughout. We want to have enough metadata about the software to be useful to determine who did what and when. So we have this data being explicitly created and consumed in our systems. We want to have enough metadata about the software to be useful to determine who did what and when, so we have an idea of what to fix moving forward. Without this data being explicitly created and consumed in your systems, it's often difficult, if not impossible, to figure out what is vulnerable or compromised and what needs to be done to fix it. It also makes everything easier when you're following open specifications around this metadata than using something that's proprietary, right? It's much easier to use these open standards, open specifications than using something that is controlled by a vendor. For example, it's generally better to use, something like Open Telemetry, which is a CNCF project, rather than using a specific vendor's closed ecosystem, since there'll usually be more support in the public for the open thing than there will be for the closed one. Now, here are some examples of open specifications, frameworks, and tooling. There are tools that either generate supply chain metadata, ingest supply chain metadata, or are used for enforcing security based on that supply chain metadata. So let's go through them. I'll go quickly. So yeah, instead of each software composition tool, the first one here, instead of using stuff like proprietary SCA reports, use stuff like SBOMs or software bills of material, right? Don't just use, a proprietary SBOM specification. Use something like SPDX or CycloneDX, which are two open specifications. Instead of just relying on ad hoc analysis of build logs, when you want to figure out something with your build, why not look at generating an in toto SALSA attestation based on the SALSA best practices? And for folks who are not familiar, in toto attestations are an open format for generating metadata about some subject, usually software. And SALSA recommends its use for proving that you're actually following the SALSA best practices. Instead of generating ad hoc exceptions in an email or through a ticketing system, use the Vulnerability Exploitability Exchange or VEX specifications like OpenVEX. OpenVEX is just a format that lets people, make a claim about whether or not a piece of software could be exploited from a particular vulnerability. It's very useful when a piece of software uses a dependency with a vulnerability, but doesn't actually rely on the vulnerable code path. Instead of using proprietary checks to determine if some project is following best practices, look at stuff like OpenSSF scorecard. Instead of enforcing custom security rules against a code repo, look at OpenSSF All-Star. Instead of having to implement security rules for GitHub and GitLab projects, explore using GitTough, which applies policy to Git irrespective of where the Git repo actually lives. Instead of throwing all this supply chain metadata into some custom database or data lake, use GUAC to ingest and analyze it. Instead of creating spreadsheets with custom controls for ingesting software, look at stuff like OpenSSF S2C2F and NIST's OSCAL frameworks. Look at using emerging specifications like CD events, which could be used for messaging between the systems in your SDLC. Instead of enforcing SDLC processes through manual runbook and ticketing mechanisms and enforcement of those mechanisms, look at using in-toto layouts that can describe these processes in a machine-readable and automatable way. Right? Instead of relying on the various tools you're using for to update things, look at an update framework like Tough, look at the update framework, also known as Tough. All right, so I know I briefly talked about SBOMs, but it's kind of the elephant in the room, right? SBOMs have almost become synonymous with supply chain security. This is a bit of a double-edged sword. On the one hand, there's a lot of good things about SBOMs. They provide a rallying call around what we're trying to do. They're standardized. However, there's also a lot of issues as well. It's too easy to think about every problem in supply chain security as something that could be solved with an SBOM, right? This has led to a lot of the SBOM specifications and tooling to become needlessly complicated. They no longer just contain information about software composition, like licenses, dependencies, and the relationships, but now they contain information about AI, about how software is actually being used, about how the software is run, how it's being built. This leads to issues with what pieces of the SBOM picture tooling support, what pieces of the SBOM tooling supports and what doesn't support, because a lot of the things I mentioned are all optional, leading to even further confusion. So here's an example of an SBOM, and this SBOM is for a component of GUAC, which we'll look at a little bit later. If we look at this SBOM, we can see a lot of useful information about, what tool generated the SBOM, who the creators of the what tool created the SBOM, when was it created, that sort of stuff. What are the checksums for important files, like, in this case, what is the checksum of the actual tool that the SBOM describes? And we also have a ton of information about the dependencies as well. This is great for a machine to read, but can be a bit difficult for a human to parse and understand. I could use tools like JQ to help parse, but this can often be too difficult to see at a glance whether or not if any of this software is vulnerable or if I shouldn't use it for some reason. Right? Now, here is that same SBOM with just it being parsed out in a different way, where we're just looking at the package names for the dependencies and their versions. So it's still, though, 150 or so packages, which, so it's still a lot to kind of grok. It's better, but it could still be a little confusing as to, if you're just looking at this, you would have to go out there and say, okay, well, is Go Crypto version 1.0.0 actually vulnerable or compromised in some way? So tools can help. SBOMs were not really intended to be read by humans in most cases, though they often are today. Tools help in analyzing SBOMs so you can better make decisions about what dependencies you include in your software supply chain. There are a ton of tools that generate SBOMs with different support for differing support for different ecosystems. Some support Python, some support Java, some support both, one better than the other. There are also a bunch of tools that can read in SBOMs and correlate that data with data in vulnerability databases to determine which, if any, dependencies have vulnerabilities. There's some tools out there that can also be used to modify, merge, and transform SBOMs. So if you, for example, want to have an SBOM for your container that also includes the data from the SBOMs from the software you include in the container, you can do that. Finally, there are relatively few tools that consume and analyze SBOM data, though there are a few like GUAC, which we'll be talking about more, and there's also dependency track as well. In addition to SBOMs, there's a bunch more metadata we need to consider, like in toto salsa attestations. This includes data about what files were included in a build, along with information on the parameters. This is very useful to help determine if anything has gone wrong from the build side of things. OpenVex, as I sort of described previously, right, helps us better understand, again, if a vulnerability was discovered, whether or not you're actually impacted. Scorecard helps us understand to some extent the health of the upstream software project for the dependencies we use. And OSV is a modern way of communicating vulnerability information in a machine-readable way, as well as being a public database of open source vulnerabilities. There's a ton more data out there, but all of these pieces of metadata are just a part of that supply chain observability puzzle. So now let's look at how the pieces come together around the metadata and security practices. So here's an example of some tools you can use to help secure your software supply chain, organized neatly into something that is akin to a sandwich. I won't go into all of them, but I do want to highlight the flow here. At the top, you have tools that are tools, frameworks, etc., that are focused on software producers. This includes SBOM, but also, in my opinion, more importantly, includes things like Salsa and Allstar. Here's where we're securing the production of software and generating metadata about that security. We then need to distribute and analyze that metadata in context. This is where tools like GUAC come into play, but also deps.dev and archivista. On the software consumer end, right, consumers want to do two main things. They want to ensure that no piece of software they're pulling in is vulnerable or malicious, but they also want to understand the software in context. If they do have a vulnerability in one place, they want to know if a vulnerability does exist in something that they pulled in, is that dependency being used by one project or 100, right? This includes, in figuring this out, this includes tools like the GUAC tooling, like the API tooling, that could help perform queries to help you better understand the impact of bringing a new dependency into your supply chain, or looking at what is impacted by a new vulnerability. This also includes frameworks like S2C2F that describe practices for safely consuming open source software, especially open source software that maybe isn't following the latest and greatest best practices like Salsa. Finally, on the left-hand side, we have the sort of rules for making the sandwich. This is where you can use frameworks like in toto to describe who is allowed to do what in your supply chain. This is also where things like SigStore come in, where we can start to verify the identities of the actors and systems within our supply chain. Now, here's another look at the approach for how to solve this problem from a bottom-up depth perspective. Here we start looking at the supply chain security activities and generating metadata for our software supply chain security purposes. And it has to start with trust. We need to answer the question, who do we trust to do what in our software supply chain? This is where, again, tools like SigStore come in. We can associate an identity, whether it's a developer, a system, or organization, with things we do. For example, was this artifact signed by an identity in a GitHub action? We can then take those identities and start to make attestations tied to those identities. This GitHub action performed this build, and that build followed Salsa level 3 practices and generated this artifact. With all this metadata being generated, we then need to analyze it and summarize it. We can utilize tools like GUAC to then answer questions. For example, how many of our dependencies are Salsa level 3 that were based on GitHub actions, right? Finally, we can then base policies and get insights from the answers to these questions. For example, introduce a policy that only allows artifacts to be deployed to production that were built by approved Salsa level 3 capable build systems. Now, let's tie it all together with GUAC. So GUAC at its core is just observability for your software supply chain. We ingest all that metadata we talked about previously, things like SPDX and CycloneDX, SBOM, salsa attestations, scorecard, OpenVex, etc., and ingest it into a database you can then ask questions of. The way this works in GUAC is we take the metadata we described and we parse that metadata, splitting into a set of nodes and edges we transform into a graph. For example, we look at the SBOMs and the relationships of the dependencies in those SBOMs to create nodes and edges, representing those relationships. As more data enters into GUAC, we can create new nodes and edges. We might ingest some info about some software from an SBOM, some dependency info from Salsa, and then include information about vulnerabilities from OSV. We also track where the information came from, which helps us better track the trustworthiness of that data. Okay, so let's look at a practical example. This comes from the GUAC docs, so if anyone wants to follow along, feel free to start at docs.guac.sh. So GUAC uses GraphQL as its primary query API. This allows us to ask questions about our supply chain. Here is an example query. In this query, we are asking GUAC for all packages that depend on the Prometheus Golang Golang client. And now we can actually look at running this. So if I go over here, I have this pre-canned, but if here, this is sort of the GraphQL playground that's connected to my GUAC that I have running, and I can execute that query. And you can see here, there's a whole bunch of information on the right-hand side. That's the list of packages that depend on Prometheus, right? And once again, this is information that can then be used by automation for stuff like policy enforcement. But now let's take actually another look at it in a slightly perhaps more human understandable way. Let me move to this slide. So here's that same sort of data in a browser visualization. We can see here that the various packages that depend on the Go Prometheus client, right? Once again, this is that same query, just now sort of in a JavaScript visualization. Now, this is a simplified visualization for the sake of the presentation here, but we can see here that like there's a bunch of different packages that depend on the Golang client. And one of the things that we have here is we can see that there's this library, which is the Go metrics library, which through 13 packages rely on the Golang client because those 13 packages rely on Go metrics, right? And so if something were to go wrong with, let's say, Go with the Prometheus Golang client, you might want to first start looking at the Go metrics, the Go metrics library, because that is the one that's most commonly used here, at least in this supply chain. Now, GUAC helps not just with what you know about your supply chain, but also helps highlight what you might be missing. Since we are recording not just the information, but where it came from, we can tell you where there are gaps. For example, do you have an in-toto salsa attestation for a particular package? All right, let's now see what data we have regarding that Prometheus client we saw in the previous example and see what we might be missing. For the sake of simplicity, I already ran this command and have listed the output. As you can see, we have information about the source and that from at least the last polling we did of the OSV vulnerability database, there's no vulnerabilities related to this Go module. We also have some links here that bring us to an experimental GUAC visualizer, and we can take a look at that now. But you can see here, for example, we don't have a salsa attestation, which is to be expected since it is just a Go module. All right, and so here is the experimental Go visualizer, and I apologize that it looks weird just because of how it's embedded in the presentation. But you can see here that we have information here, and I can also figure out more stuff about what exists under the Prometheus, thing here, and we have all the versions that we have information about regarding, for example, client Golang. All right, let's also look at a known package that does have a salsa attestation. So here's one. In this particular case, it is going to be some Kubernetes related artifacts that are inside of that we have information on, and we have a salsa attestation for this version of, in particular, kubectl. And we can also now run another GUAC query on this. So I know that, once again, based on this, I have information that it is, actually I have a typo there, that it is package 6363 that I have information on. And so if I go over here, I can query that node and find all the information about it. And here's a bunch of information about the salsa that we have. And if I go in now next to the visualizer again, I can go in and see it in a slightly different context. Let me zoom out here a little bit. There's still a lot more here to be done, right? So actually, hold on 1 second here. So as you can see here, so this is information we have that's based on the salsa. If I want to go in and see what additional information I have about, for example, this krel package over here, I can go in and click, over here. And so this is information regarding the Kubernetes release for 1.24.1, which we have. And once again, it's a little hard to read, but you can run this yourself as well. All right. Okay. And let me go forward a bit here. 1 second. Oh, it looks like the slide got cut off here. 1 second. All right, so now let's look at next steps, right? So there's still a lot more that can be done. GUAC can use some more contributors and users. There's still a lot more work to be done in the tooling space, especially around policy enforcement. Finally, there's also movement around what folks are calling an SDLC, or software supply chain control plane, which would be a tool similar to, think of it like Kubernetes, how Kubernetes is an API for orchestrating usually container work. The need for an API that helps orchestrate the supply chain. And so, yeah, that's my presentation. I know it's pre-recorded, so I don't get to, I can't ask for, or you can't ask any questions, but feel free to, reach out to me. I'm available in, OpenSSF Slack, usually in the GUAC room. I'm also available in the CNCF Slack, and I'm sure the organizers can also help forward along any additional questions you might have for me. And yeah, thank you for having me, and I hope you have a good rest of the little sort of virtual conference here. Thanks.